In this video, I'm going to show how to draw the shear and bending moment diagrams for a beam that has a load of 10 pounds on the left-hand side, as you can see, as an additional of 20 here, and then it has reactions of 25 and 5. And again, I went ahead and computed the reactions so that we can just focus more on the shear and bending moment diagram itself, not so much on equilibrium for the beam. Now this approach is a little different than the approach that we did in an earlier video in which we went through and made cuts at various points along the beam and applied equilibrium. This approach uses two fundamental concepts that we covered in the lesson material online. The first of all is that any change in shear between 2 points is equal to the area under the loading diagram. Okay, and again, this will be a little more self-explanatory as we go through it. The second relationship that's really important is that a change in bending moment between 2 points is equal to the area underneath the shear diagram. So let's just go ahead and kind of jump into this, and then we'll apply these two concepts as we go through. The idea that we're going to start with is, say we have a little man here. I'll start with a man, okay? And he's going to walk across this 15-foot long beam. He's going to start at the left, and he's going to work his way across, okay? Well, when he starts, he sees right off the bat that he has a 10-pound load going down. So our shear at this point is automatically minus 10. Again, it's minus because it's going down, right? Just using the standard convention that going up is positive, going down is negative. Okay. Now, as he walks his way across the beam, we want to know how shear varies from, for example, x equals 0 to a distance of x equals 5. We see here from the first concept that the change in shear between 2 points is equal to the area under the loading diagram between those points, okay? Moving from the 10-pound load to the 25-pound reaction, there is no loading area here. We just have 2-point loads, okay? So the shear is going to be constant as he walks all the way across right to a distance of 5 in which he encounters his 25-pound load, okay? So the 25-pound reaction, when you start with a negative 10, now we're going to go up 25, gives us a value of the shear right here of 15. Again, that would be the minus 10 plus 25. Let me draw this a little deeper here. There we go. Hopefully that shows better. Okay. Now again, as he works his way across the beam, okay, he's walking towards the right. And again, there's no change in shear because, again, for there to be change in shear, you have to have some type of area under the load diagram. But we have no area under the load diagram because we just have point loads. So shear is constant. Okay. Then he gets to this load of 20 pounds. Again, if he's at 15 right now, he goes down 20. Okay. This puts him at a value of minus 5. So I'll put this right here, minus 5. Okay. And then again, as he walks his way from the 20-pound load towards the reaction of 5 pounds, it's going to be constant because there is no area under the load diagram. Okay? And that essentially is what the shear moment diagram, what the shear diagram looks like. Now, for us to compute the bending moment diagram, we're going to use this relationship that the change in bending moment between 2 points is equal to the area under the shear diagram. So, for example, if this distance here is 5 feet, we have 5 feet here and 5 feet here, okay? The change in bending moment, okay, from 0 to 5 is equal to the area underneath the shear diagram, right? This area here is minus 50, right, because we have 5 times minus 10. Likewise, the area has of this rectangle has a base of 5. This value here is 15, so we have an area of plus 75. And then the area here, we have 5 feet with the value of negative 5. This area here would be minus 25. Okay. So the change in bending moment between 2 points is equal to the area. So we know, for example, from going to x equals 0 to x equals 5, that the total change is minus 50. Okay, so we have this value down here, okay, of minus 50. Now the question is, how does it change? Is it a linear relationship, a straight line relationship? And for us to understand that, all we have to do is think about this in terms of taking one slice at a time. If we took one slice of this, say for example we took this piece right here, which was 1 foot wide by minus 10 deep, right? We would have a value of minus 10. If we made it 2 feet wide by minus 10 deep, we'd have 20. So you can see that there's a linear relationship, right? As you move from x equal to 0 to x equal 5, it varies. The change in moment is going to be a linear relationship. Okay, so straight line, but linear relationship. Likewise, the same analogy is here. For example, when you move, if you go 1 foot here, 1 foot wide by 15 tall would be 15. If you had 2 feet wide, right, by 15 tall, you'd have 30. So again, this is also a linear relationship. So if we're starting from minus 50 and we're gaining an area of plus 75, I'm going to circle these values here real quickly. So we go up 75. Okay. That gives me a value right here. If I was minus 50 and now I went up 75, this gives me a value of 25. And the units on that would be foot-pounds. Likewise, these are foot-pounds. Okay. And then from here, as I go from this distance out to here, so x equal 10, all the way out to x equal 15, again, for every foot that you move over, there's a linear relationship that explains the change in bending moment. Okay. So essentially what we have is we have a shear diagram, right, that looks something like this. Right? We have with a maximum negative shear of minus 10, a maximum positive shear of 15, and then we have a bending moment diagram, right, that looks something like this, where we have a maximum bending moment of minus 50, and the negative side, then a positive bending moment of 25. And again, so all we did in this example is, rather than make cuts like we did in part 1, we just used these two fundamental concepts to actually compute what the shear between 2 points would be, or what the bending moment between those 2 points would be, and derive the diagrams that way. And that concludes this example.